Okay, I'm vibrating. I am vibrating with an amount of caffeine that is probably medically inadvisable, but honestly, it is completely necessary. Because today we are not just, wading into the shallow end of the data pool. We are strapping on the heavy diving gear and going straight to the bottom of the Mariana Trench.
Please tell me you didn't actually drink that entire pot of coffee before we started recording. You look like you're about to literally phase through the desk.
I plead the fifth. Look, we have a TAP study session to get through, and the energy needs to be high. We aren't just browsing headlines for this deep dive. We are tackling the absolute leviathan of big data.
Leviathan is a good word for it, honestly.
Yeah.
We're dealing with the framework that effectively taught the internet how to think at scale. But before we get to the monster, we have a very specific tradition to uphold.
We do. A massive, highly caffeinated shout out to Niu, for absolutely smashing his January exams. We see you, we appreciate you, and we hope you're taking a nap right now because you earned it.
Seriously, congratulations, Niu. That is no small feat. Now, speaking of smashing through massive amounts of work, are we ready to talk about the elephant in the room?
Pun fully intended. Yes, we are talking about Hadoop. And
Right.
yeah, for everyone listening who pictures this sleek, futuristic server farm, you should actually just be picturing a yellow toy elephant.
Right. It was literally named after the creator's son's stuffed toy.
Yeah.
But don't let the cute name fool you. This framework is essentially the backbone of how we process the modern internet. It's the difference between managing a spreadsheet and managing the Library of Congress.
If the library was on fire?
Yeah, if it was on fire and expanding by 1,000,000 books a minute.
Exactly. So our mission today for this deep dive is to decode the holy trinity of the Hadoop ecosystem. We've got the storage layer, which is HDFS. We've got the processing engine, MapReduce. And we've got the management, which is Yarn.
Storage, processing, and management. It's the classic stack. Let's start with the foundation, HDFS.
The Hadoop distributed file system. Now, I used to think saving a file in Hadoop was like saving a Word doc on my laptop, just, bigger. But looking at the source docs, that is completely wrong.
Oh, it is a completely different architecture. If you try to use HDFS like your laptop hard drive, you will hate your life.
Yeah.
Your laptop is designed for low latency, opening a specific file, saving a photo. It works in these tiny little blocks, usually about 4 kilobytes.
Right, tiny little grains of sand.
Exactly. But HDFS is designed for high throughput. It's designed to stream massive amounts of data. So the default block size isn't 4 kilobytes. It's typically 128 megabytes.
That is massive. That's like using, shipping containers instead of cardboard boxes.
It is, and there is a physics reason for that. Hard drives, traditional ones anyway, are mechanical. Moving the read and write head to find a piece of data takes time. That physical movement is called seek time.
And seek time is expensive, right? Like it's wasted time.
Incredibly expensive. If you have a petabyte of data, you don't want the drive head buzzing around looking for millions of tiny files. You want to find one massive chunk, that 128 megabyte block, and just read it continuously. You want to maximize the actual transfer rate and minimize the seek time.
Okay, so we take this massive file, we chop it up into these giant 128 megabyte Lego bricks, and this is the really cool part, we don't just put them on one supercomputer, we scatter them.
Right. We scatter them across commodity hardware. That's the industry term you'll see in the docs.
Which is really just a nice corporate way of saying cheap servers.
Relative to a $1 million mainframe, yes, cheap servers. These are the datanodes, and you might have thousands of them in a cluster.
But here's the problem, and I really want to unpack this because it blew my mind. If I have a petabyte of data scattered across 1,000 cheap servers, and I want to run a program to analyze it, if I try to pull all that data to my local computer to process it, the network is just going to melt down.
That's the primary bottleneck, network bandwidth. In a massive data center, moving data around is the single most expensive thing you can do in terms of time. It is literally like trying to drink a swimming pool through a cocktail straw.
So Hadoop just flips the script. The source material calls this the golden rule of locality.
Yes. Moving computation is cheaper than moving data. That is the fundamental mantra of Hadoop. Instead of pulling the heavy data to the software, the master node, the Namenode, looks at its internal map and says, okay, the data blocks you need are sitting over on server A, server B, and server C.
And then it just sends the code, like the tiny little Java program, directly to those servers. It's like instead of bringing the entire library to your house to write a research paper, you just send a photocopy of your essay prompt to the library.
That's actually a great analogy, and the scheduler is extremely smart about this. It has a strict hierarchy of preference. The absolute best case scenario is what we call data local.
Meaning the code runs on the exact same physical machine where the data block is currently sitting on the hard drive. Zero network traffic.
Exactly. The CPU talks directly to the local disk.
Yeah.
Beautiful. But, sometimes that node is busy. Maybe it's already running another job. So the scheduler moves to the next best option, which is rack local.
So it runs on a different server, but one that's in the exact same physical metal rack. So they share a top-of-rack switch.
Right. It has to hop over a wire, but it's a very short hop. It's fast, but not instant.
And then the absolute worst case scenario is off-rack, where you have to go across the main data center switches. And Hadoop will just do everything it can to avoid that, right? Because it guards bandwidth like gold.
It has to. Because once you saturate the core network switches, every single job in the cluster slows down.
Okay, so we've got our data scattered, and we're sending code directly to it. But who is acting as the traffic cop here? Because reading about the old days, like Hadoop 1.0, it sounded like an absolute nightmare.
Oh, it was a dictatorship. In Hadoop 1.0, you had a single central service called the job tracker. It did everything. It managed the physical resources, the CPU, the RAM, and it also managed the life cycle of every single job.
And because it was doing literally everything, it became the bottleneck. If the job tracker got overwhelmed, the whole 1,000-node cluster just crawled.
Exactly. So in Hadoop 2.0, they realized they had to decouple this. They introduced Yarn.
Which stands for, wait for it, yet another resource negotiator. I mean, come on. That is peak developer humor. Just, we needed a name, we were tired, here you go.
It's descriptively accurate.
Yeah.
But it really was a game changer. Yarn split the responsibilities. Think of it like a massive corporate restructure. HDFS is just the bucket. It holds the data, MapReduce is the worker, it does the specific application logic, but Yarn is the operating system of the cluster.
So Yarn creates this clean separation. You have a global resource manager that knows where all the RAM and CPU cores are in the entire data center. And then on every single machine, you have a node manager.
Right. And this was completely revolutionary because it meant you weren't just limited to MapReduce anymore. Because Yarn is just a neutral party negotiating resources, you could suddenly run other applications like Spark or Flink on the exact same hardware at the exact same time.
It turned Hadoop from a one-trick pony into a fully multi-purpose data center.
Precisely. But even with Yarn managing the hardware, we still need to talk about how the actual work gets done, the classic processing model, MapReduce.
Okay, yes. We need to talk about MapReduce because I was reading through the logic of how the map phase works, taking an input and processing it in parallel across all these nodes, and then the reduce phase, which combines it all. And, well, I had a realization.
Oh, no. I know that tone. What is it?
I realized that MapReduce is basically a shinobi mission.
I'm so sorry, what?
No, hear me out. It is literally Naruto's Shadow Clone technique, Kage Bunshin no Jutsu. Think about it. You have a massive task. You can't do it alone. So what does Naruto do? He creates 1,000 clones.
Okay, I see where you're going with the parallelism, but...
It's totally distributed. Each clone is a separate node doing its own task, fighting, training, whatever. They are running in parallel. And then when they poof away, which is the task finishing, the main node, Naruto, gets all the data, all the experience back. That is MapReduce.
Okay, I have to stop you there. I appreciate the enthusiasm, and it works for the scatter-gather visual, but technically...
Don't you technically me on my own anime metaphor?
I have to. Technically, though, they share one chakra pool. That's more like threads sharing a single CPU's memory. If one clone hits a race condition, Naruto's getting a massive headache.
Okay.
In Hadoop, the nodes share nothing. They're completely separate physical servers. One node can catch fire and literally melt down, and the other nodes have no idea. They don't share memory, they don't share chakra, they only communicate by sending messages over the network.
So you're saying Naruto is a multi-threaded application, not a distributed cluster?
Unless Naruto is running a separate Java virtual machine on every single clone, yes. Your metaphor is buggy.
Fine. We agree to disagree. But I am still picturing the mapper tasks wearing little headbands.
I can live with that. But let's actually look at what happens between those clones and the final aggregation, because that is where the real complexity of the framework is, the shuffle.
The shuffle. Which sounds like a fun dance, but the documentation makes it sound like a logistical nightmare.
It is the absolute heartbeat of the MapReduce engine. And it's the only time the cluster really hammers the network.
So the map task finishes its job. It has processed its local block of data, but it doesn't just instantly send it across the wire to a reducer.
No, if it did that, the network would be instantly flooded with millions of tiny packets. Instead, each map task has a buffer in its memory. It's a circular buffer, usually about 100 megabytes by default.
And when that buffer gets full, I think the docs say 80% full, it spills to the local disk. But before it spills, it does something really important. It sorts.
This is critical. It partitions the data, meaning it decides exactly which reducer each piece of data is going to based on the key, and then it sorts it in memory.
But why the sort? Why spend the compute time?
Because the reducer fundamentally relies on it. The main guarantee of MapReduce is that when the data reaches the reducer, the keys are perfectly sorted. This allows the reducer to easily merge massive streams of data without having to hold everything in memory and search through it again. It's like sorting your mail by zip code before you put it on the delivery truck.
Okay, so the map task writes these sorted partitioned files to its local disk, and then the reducer wakes up and says, hey, I need my mail.
And that fetch is the shuffle. The reducer reaches out across the network to all the different map nodes, and there could be thousands of them, and pulls the specific partitions that belong to it.
And since there might be thousands of mappers and dozens of reducers, this is an all-to-all communication pattern. It is a massive amount of cross-cluster traffic.
Which is exactly why tuning that buffer size and managing how often it spills to disk is so important for performance. If you spill to disk too often, your job slows down because disk I/O is slow. But if you run out of memory, you crash.
Speaking of crashing, that actually brings us to the reality of the hardware. The source material is surprisingly cynical about this. It basically says, hardware failure is the norm, not the exception.
That's the core Google philosophy that Hadoop adopted. If you have 10 servers, you might go a year without a single failure. But if you have 10,000 servers, you are mathematically guaranteed to lose a hard drive or a motherboard every single day.
So the system can't panic when a server dies, it just has to expect it. But how does it know? Does the dying server send out a distress signal?
Actually, it's the exact opposite. It's a heartbeat. Every date node sends a tiny signal to the name node every 3 seconds, basically saying, I'm alive, I'm alive.
And if the name node suddenly stops hearing that beat?
It waits, usually for a default expiry interval of 10 minutes. It doesn't want to panic over a temporary network blip. But if it hasn't heard a heartbeat in 10 minutes, it declares the node permanently dead.
Rest in peace. But what about the data on that node? Is it just gone?
This is where replication saves us. By default, every single block of data is copied to 3 different places in the cluster.
Oh, right. So if node A dies, the name node checks its map and says, don't panic. Perfect copies of those logs are sitting right over on node B and node C.
Exactly. And it immediately orders the cluster to create a new copy on a healthy node to bring the replication factor back up to a safe level of 3. It heals itself automatically.
That handles the storage side. But what about the actual work? What if a node dies while it's in the middle of a massive map task?
The application master, that's the specific manager for that one job, sees the failure. It simply finds another node that has a replica of the data and starts the task over again from scratch.
So it just reassigns the homework to a student who is actually in the classroom.
Basically, yeah. But there is actually a weirder scenario than a fully dead node. What about a zombie node?
A zombie node? That sounds so much worse.
It really is. A zombie node is a server that isn't actually dead, so it's still sending its 3-second heartbeats, but it is running incredibly slowly. Maybe the physical disk is failing and reading at 1% speed, or the CPU is thermal throttling.
Oh, I see the problem. Because if the system thinks it's alive, it just waits for it. And your whole petabyte job gets stuck waiting for this one incredibly slow straggler to finish.
Exactly. This is known as the long tail problem. You have 99% of your job done, but you are sitting there waiting 20 minutes for the final 1%.
So how do we kill the zombie?
With speculative execution.
Man, I love this term. It sounds like high-stakes Wall Street trading, but it's just computer science.
It kind of is like trading. The system actively monitors the progress of all running tasks. If one task is dragging way, way behind the cluster average, the scheduler essentially hedges its bets.
It launches a backup copy of the exact same task on a completely different healthy node.
Right. Now you have a race. The original slow task versus the new speculative task.
And the winner takes all.
The first one to successfully finish commits its output. The loser is immediately killed.
It is brutal, but so efficient. It just ensures that one bad hard drive doesn't delay a massive job by an hour.
Exactly. It's all about ensuring reliability at scale.
Well, okay, we have mapped, we have shuffled, and we have speculated. I think our brains are sufficiently distributed at this point, which means it is time for our absolute favorite segment.
Oh no.
Oh, yes, the Japanese word of the day.
I am already pre-cringing for the comments section.
Today's word is thematic, though. The word is kogiki.
Kogiki.
Or is it kogiki?
I think it's kogiki. It means attack.
Right. And while it's usually used in anime for, physically punching people, in our context today, we're talking about a cyber attack or an aggressive data processing load, like attacking a computational problem with 1,000 nodes.
To all the fluent speakers and the subs versus dubs elitists listening right now, we are so sorry.
Our pronunciation is honestly cursed. Please send help in the comments. We are trying our best over here.
We really are. But speaking of the comment section, we actually have a quiz for you today, a little test of your attention span.
Let's hear it.
We mentioned earlier that in a standard Hadoop cluster, the default replication factor for a data block is 3. We told you that means there are 3 copies for safety. But the question is, why is the default specifically 3? And how exactly are they placed across the cluster?
Ooh, that's a good one. It's not just random. There is a very specific logic to where those 3 copies go to balance safety and network speed.
So if you know the placement policy, exactly where the first, second, and third replicas go, let us know in the comments if you know why it's that specific number.
All right, we've mapped it and reduced it, but we aren't done yet. What CS topic is haunting your dreams? Graph databases, Rust, assembly. Let us know what we should tackle next in the comments.
And before you go, make sure to commit to this channel. Go ahead and push that like button and pull a subscription into your feed so you don't miss the next murd. Let's keep this repo clean, people.
Oh, yeah.